Guys, welcome to our channel of Sciences and Mathematics. My name is Ernest. Today we are going to look at a concept in chemistry, and that is the role of catalyst in chemical reactions. So in this case, we are going to look at some of the energy level diagrams that I've drawn on the board and try to do a comparison between the ones that we have already discussed, which of course may lack some basic features that I've demonstrated for today. So we're going to look at what necessitates the presence, or why should we include such features whenever we're trying to do an energy level diagram for chemical reactions. So for today, we're going to look at the role of catalyst, and then we shall look at the different types of catalysts and perhaps the role of enzymes and some of the reactions that we may be able to demonstrate using the effect of catalyst, basically using the concept of maybe a stoichiometric equation and some of the conditions which we may treat as a catalyst, like the effect of enzymes and light. So for that case, thank you and welcome. So as I've said, today we're going to look at the role of a catalyst. Now I've drawn these two sets of energy level diagrams on the board to set a base for us, for our discussion for today. This basically is because I understand that as we're going to proceed with the role of a catalyst, it's better for us to have an illustration so that we can be able to understand basically what a catalyst is. Now this is going to entail the concept of activation energy, which I've of course not shown in some of our videos that we have drawn using the energy level diagram. Now suppose I use this lower space here. We have been illustrating the energy level diagram using this specific small graph that I can be able to indicate here. Now for exothermic reactions created using this particular concept, whereby this is the change in enthalpy, and these are the reactants, and these are the products formed. Now this is for exothermic reaction, and for endothermic reaction we're going to see that this is going to change direction, and we shall have a graph that is showing this is energy against the reaction path, and then we have the reactants and the products which formed for endothermic reaction. Now this is positive, negative. Now in this case, when this particular energy level diagrams, we are trying to put them like this, they do not have this section of the curve that I'm trying to illustrate. These two setup, let's call this one setup A and B. So I've drawn this section of the curve that has got a raised point, that particular point. So I want to show the difference between this illustration and this one, in a sense that we have obviously been omitting this case for this specific discussion. Now whenever chemicals reacting to form products, there's a minimum amount of energy that is required by the reactants in order to enable the products to be formed. Now this minimum amount of energy that has to be possessed by the reactants for chemical reaction to take place is referred to as activation energy. So in a sense, this is the minimum amount of energy that reactant must possess for chemical reaction to take place. So basically this is what I've illustrated using this section of the graph for exothermic reactions and endothermic reactions respectively. Now in trying to compensate for the enthalpy or the heat that is either absorbed or released from the system, this activation energy does not entail that amount of heat. Of course, for this kind of reaction, like an exothermic reaction, we're going to account for the change in enthalpy only using this section of the curve. So therefore the net heat that is released from the system is just from this part of the graph to this one. And for the endothermic reaction, we're going to see that the activation energy can be represented as such, and the net heat in this particular case is going to be from that section to this one, and and that is the heat that is absorbed into the system during the chemical reaction. So the illustration for these two graphs, of course, is going to get improvised, in a sense that when we introduce another substance that is going to speed up the rate of a chemical reaction, this graph is going to change and it will be represented as, for endothermic reaction, we're going to have this graph represented as such, and this one will be represented as this. So in this case, basically, if we try to see there's a net decrease in the amount of energy, whereby this one there's a net decrease, and then for the lower one there's a net decrease the amount of energy that is required in order for this reaction to proceed. So this change in energy can be able to be achieved by using a substance that we refer to as a catalyst. So therefore, a catalyst is a substance that reduces this energy that is required in order to ensure that the reaction proceeds. Therefore, this has got a resulting effect of increasing the rate of a chemical reaction, and that will basically consist the role of a catalyst. So therefore, we can be able to define a catalyst as a substance that increases the rate of a chemical reaction, whereby in actual sense this specific substance is not consumed or maybe altered during this chemical reaction. So basically we're going to look at different types of a catalyst. Now from the two illustrations, I hope that we have understood the effect of a catalyst when it has been introduced either in an exothermic or an endothermic reaction. Now in our second illustration, we're going to see different types of catalysts and how they can be able to influence or maybe try to be used in this case of endothermic, exothermic reactions or different manufacturing processes in order to achieve the desired product. So I'm going to do away with this so that we can be able to look at types of catalysts that we have. So basically, I'm going to look at types of catalysts. So we have basically two broad categories of catalysts. The first one is known as, or maybe we can categorize them as heterogeneous, and number two as homogeneous types of catalysts. Now for heterogeneous types of catalysts, these are catalysts which are different in physical state. You can just do away with this. These catalysts are different in their physical state as compared to the reactants or the reacting species. For example, we can have one of the catalysts that is used in the manufacture of sulfuric acid. Basically this is the second step for manufacture of sulfuric acid, whereby we have formation of this. So this is a gas, and this is a gas. So in this case, when this reaction is taking place, we're going to see that we can just have a stoichiometric form of that equation. We're going to see that there is going to be involving the use of vanadium 5 oxide, which is basically going to act as a catalyst in this case. But there's a unique way in which we're going to see this. If we try to look at the reactants and the products, both of them are in gaseous phase or gaseous state, but this is going to be a solid catalyst. Therefore, from our broader definition for the two, we're going to refer vanadium 5 oxide as a heterogeneous catalyst, since it is different in phase compared to the phases of the reacting species. So in this case, this is one of the examples of a heterogeneous catalyst, and we're going to see that for solid catalyst like vanadium 5, basically they are more effective when they are in powder form, since this one increases the surface area for reaction. Now this one is achieved through the fact that these types of catalysts react from the concept of a adsorption process. Now adsorption means adhering or adherence to the surface of maybe a reactant, and we're going to see that as compared to the solid, a powdered form has got a large surface area, so therefore the level of adsorption is going to increase when the substance is in powdered forms. Therefore the catalysts which are in solid state are more effective when they are in powder form, because they form a large surface area upon which a reaction is going to take place. Now the second category of catalysts that I mentioned was homogeneous catalysts, and this basically are just the opposite of the first one that we have talked about, whereby the reactants and the catalysts are in the same physical state. This implies that they can be both solids they can as well be a catalyst can be a liquid and the reactants liquids, and lastly the catalyst can be gaseous or maybe a gas and the reactants are gases. So basically whenever we have these three conditions, then we refer to that kind of a catalyst that is in that state as a homogeneous catalyst. And we're going to see that both of these catalysts can be able to facilitate a large reaction, depending on maybe it is independent of the amount of catalyst. So therefore a small catalyst can be able to initiate a very large amount of a chemical reaction, or maybe an enormous amount of reaction. So examples of common catalysts that we normally use in industrial processes, you can be able to name a few for illustration purposes. So we're going to look at a few, some examples of the catalysts that we use, which we can be able to relate to. So the first one is iron. This iron is used in manufacture of ammonia in the Haber process. So basically during the manufacture of ammonia we have nitrogen reacting with hydrogen gas. This is a nitrogen plus hydrogen reacting to form ammonia. So we're going to form a stoichiometric equation using this one. So this is a gas. So from this one we're going to see that this specific kind of a reaction is reversible, so we can just represent it using arrows as that. And there are other conditions which of course may accompany iron in this state, like the temperature and pressure. So when we are talking about some of the conditions that facilitate the rate of reaction in chemical kinetics, we talked about the concept of temperature, pressure, catalyst, and then we also talked about other aspects like the temperature, pressure, the catalyst, and also we talked about the concept of concentration of reactants and the physical states. So maybe just to mention physical. I've talked about the effect of a solid catalyst, so maybe I can talk about the concentration of the reactants. And these were some of the aspects that we looked into in chemical kinetics, which are affecting the rate of a chemical reaction. So in this case, we're just limiting ourselves to the concept of a catalyst, whereby this Haber process employs the concept of a catalyst, whereby iron is used as a catalyst. Another of the examples of a catalyst that I've already mentioned is the manufacture of sulfuric acid, whereby the first step entails burning of sulfur. This is step 1, and then our combustion of that. And then step 2, we're having sulfur 4 oxide still undergoing that process to form that product. So we're going to see that this is going to have, so we can just write this one as 2, and then 2, this is 4, 6. So this is a gas, 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 and then we're going to have vanadium 5 oxide being used as a catalyst in this process. So this we've already discussed this one as an example of a heterogeneous catalyst, and that's one of the applications of a catalyst that we can be able to mention. And now the next one that we can mention maybe is hydrogenation of fats. Now this basically we just look at it in organic chemistry, but I can just give an example to illustrate that process for hydrogenation of fats. And this basically entails the concept of alkenes undergoing hydrogenation to form saturated compounds. So we're going to have this one plus hydrogen, whereby we're going to use nickel catalyst to form this particular product. Like that. So this is a vegetable oil. General representation of a vegetable oil that is unsaturated. I mean, which is basically unsaturated, and this is saturated. I hope we understand the concept of saturation and unsaturation when we talk about the concept of alkenes and alkanes. Now that we have talked about these two family groups of organic compounds in our introduction to organic chemistry in one of our videos. So I'm going to put a link in the description box so that we can be able to do a reference. Now, lastly, we're going to look at an enzyme, which we can basically categorize as one of the applications of a catalyst, whereby we have glucose that is maybe undergoing a process to form ethanol plus carbon 4 oxide. So this word equation can be able to be represented in form of a chemical equation, whereby we have glucose, and then we have yeast that is forming ethanol C2H5OH aqueous, and then plus carbon 4 oxide. So this is a gas. So in this case, this is one of the reactions that is going to entail the concept of enzymes, and we're going to see that an enzyme from which basically we discuss in some of the topics in biology refers to a protein. These are proteins that act as a catalyst in biochemical reactions. So basically that's one of the applications of enzymes. Now from that we're going to, of course, try to see how we can be able to illustrate the effect of light on some of the reactions. Now that we talked about the concept of light acting as an enzyme in some of the chemical reactions, like the natural processes of photosynthesis, etc. Now basically I'm going to use two sets of illustrations in order to try and discuss this particular section of our topic for today. So basically these four sets of experiments are going to assist us to illustrate the effect of light as a catalyst on some of the reactions. The first setup for A, I've done one of the examples for the formation of silver bromide, and basically this reaction we're going to see that from setup 1, 2 and 3 is going to react or maybe take place under specific conditions. Now if this specific reagents for that is potassium bromide and silver nitrate are placed in a dark cupboard. There's going to be no color change in this case. So basically this one is yellow in color, so there's not going to be any color change if this one is the reactants are placed in the dark cupboard. And number two, these ones are placed in the bench where there is partial light. So therefore there's going to be a slight change in color from basically a change in color from yellow to gray. And this happens basically because there's a reaction that is taking place between the potassium bromide and the silver nitrate, whereby there's a formation of a metallic silver that is gray in color. So the last one is a setup that has been placed in direct sunlight, and there's going to be a change of color from yellow to dark gray, and that one makes it possible for the reaction to take place in totality. So basically that one happens because of the presence of light, and from the reactions mechanism in this we have talked about the concept of energy that is involved in reaction, and this basically energy is going to facilitate increase in the rate of collisions per unit time for these molecules of potassium bromide and silver nitrate, and these collisions are going to facilitate reaction, of course, between those specific reagents, and therefore this lead to the formation of silver bromide, which I've indicated as solid in this specific case. So from this particular illustration, we can see that as we change the intensity of light, it's going to increase the rate of reaction, and therefore light is very essential in this kind of application, maybe in facilitating some of the reactions to take place. So for the second setup also is one of the ways in which we can be able to achieve a reaction between chlorine and hydrogen, that is in the presence of ultraviolet light, which acts as a catalyst. Now in setup C, this is a common biochemical reaction that takes place, which is basically photosynthesis, which is a process by which plants make their own food. Now in this reaction, there's a reaction between carbon dioxide and water, which are resulting in the formation of this is sugar and oxygen. So from this we can see that there's a presence of light that is needed for this specific two reagents to just combine to form those products, and therefore the involvement of light in photosynthesis or in facilitating that chemical reaction, of course, acts as a catalyst. Now the last one is bromination of methane, whereby the reaction does not take place in darkness but basically in light. It is an explosive process. So therefore from these two illustrations that we have illustrated on the board, therefore we can see that in the presence of light, the reactions are cutting across, the reactions are taking place as required, but in the absence of light, we're not going to have these reactions, of course, proceeding. So therefore, in trying to figure out the role of catalyst in this kind of a reaction, we are going to see that some of the reactions may require these specific conditions while others may not. Now from our illustration, we showed that the effect of a catalyst on a reaction in summary can be able to be represented maybe for an exothermic reaction by lowering this specific curve for activation energy. So this one works in the same particular sense in that it's trying to provide some energy for reactants, which basically is going to act as activation energy for the reactions to proceed. So I hope that we have understood the types of what a catalyst is, the types of catalysts that we have mentioned, and maybe the effect of light on some of the reaction. Now for the sake of the reagent, the enzyme that we mentioned about, we're going to see some of the examples, especially when we are trying to deal with some of the biological or biochemical equations that we are going to discuss in our concepts and topics in biology. So for that case, I hope that this is going to assist us again to tackle maybe some of the concepts that we may come across, which involves either directly or indirectly the effects of enzymes. So that is it for today, guys. By God bless.